What if I told you there's this hidden language that underpins pretty much all of modern science and technology, even your daily life? I know, it's not code, it's not English, it's the language of measurement. And today, we're going to learn how to speak it.
Just think about it for a sec. Your height, how long it takes to get to work, the temperature outside. We are constantly measuring, all the time, trying to make sense of the world. But what would happen if we all described those exact same things differently?
Just imagine trying to plan a mountain climb if one person is talking in feet, another person's using meters, and a third is thinking in miles. It's the same mountain, right? But the numbers just create total chaos. To build anything, to explore, to do any kind of science, we've got to be on the same page.
And this is the solution. It's called a unit. It's our agreed-upon standard. It's how we take a fuzzy idea like length and give it a real, concrete value we can all share. And that is the key. Without this simple agreement, building skyscrapers, sending probes to Mars, or hey, even just sharing a recipe online would be basically impossible.
So, how did we do it? How did humanity get from total measurement chaos to a single, universal language of reality? Well, that's the story we're going to get into in our first section here.
So this journey to a unified system, it wasn't instantaneous. It didn't happen overnight. For a long time, different systems were all living side by side. You had the CGS system, which was based on the centimeter, gram, and second, super popular in a lot of scientific fields. Then came the MKS system, which scaled things up to the meter and the kilogram. Each one was a step forward, a refinement that led us to the global standard we all rely on today.
And that brings us right up to the modern standard, the SI, or the Système International. It was adopted back in 1971, and it's being updated all the time. This is way more than just a system. It's the absolute bedrock of our interconnected world. It's the shared language of all science, all technology, and all commerce.
So, what is this language made of? Well, just like the English alphabet has 26 letters, the entire SI system is built on just 7 fundamental or base units. Think of these as the absolute building blocks for describing our entire physical world.
And here they are, the complete alphabet. You've got the meter for length, the kilogram for mass, the second for time, all the way down to the candela for luminous intensity. And here's a fun fact for you. 1 candela is roughly the brightness of a single ordinary candle. With just these 7 units, that's it. That's all you need to describe literally anything in the universe.
And this is what makes the system so brilliant and so powerful. Every other measurement you can think of, speed, force, energy, pressure, it's just the word that's spelled using combinations of those 7 letters. We call these derived units, and every single one of them traces right back to that core set of 7.
Okay, so we've got the alphabet, but just knowing the letters isn't enough, right? You also have to know the grammar. And in the language of measurement, that grammar is all about precision. And its rules are governed by this thing called significant figures.
And this is so important. Significant figures are basically how we stay honest in science. They tell you exactly which numbers in your measurement you can trust completely, and they pinpoint the very first one that has a little bit of guesswork in it. It's like a built-in code for telling you how good your measurement really is.
So let's break down the rules. The first one is super straightforward. If a 0 is sandwiched between 2 non-zero numbers, like that 0 and 48, it always counts. It's significant. It's a real measured value. So in this case, we have 3 significant figures. Simple enough.
Now, this is where it can get a little bit tricky for people. Those zeros at the beginning of a number that's less than 1, like in 0.0091, they are not significant. They're just placeholders. All they're doing is showing you where the decimal point is. The only digits here that actually mean anything are the 9 and the 1. So that gives us 2 significant figures. And this is the final key rule you gotta know. Zeros at the end of a number, they only count, they're only significant if there's a decimal point somewhere in the number. So if you just saw the number 120, we'd be a little unsure about that 0. But if you see 120.00, well, those last 2 zeros are there for a reason. They are telling you that you measured with precision all the way out to the hundredths place. They are absolutely significant.
And these rules really matter when you start doing math. See, when you multiply or divide, your answer can only be as good as your least precise measurement. It's the weakest link in the chain. So let's say you measure a piece of wood that's 2.5 meters long, that's 2 significant figures, and you multiply it by a width of 3.42 meters, that's 3 sig figs. Your calculator is going to spit out 8.55, but because your least precise number only had 2 sig figs, your final answer can only have 2. You have to round it to 8.6. It's all about not claiming you're more precise than you actually were.
All right, now for the really cool part. Once you truly understand units, you kind of gain this superpower, the ability to check if a physics equation is even possible. It's called dimensional analysis, and honestly, it's like having a spell checker for reality itself.
So to do this, we have to reimagine our 7 base quantities, not just as units, but as fundamental dimensions of the physical world. We represent them with these bracketed letters. So length becomes L, mass is M, time is T, and you get the idea.
And here it is, the one simple rule that governs everything. It's called the principle of homogeneity. It's really just a formal way of saying you can't add length to time or mass to temperature. You can't add apples and oranges. It means every single term in a valid equation that's being added or subtracted has to have the exact same dimensions, period. Okay, let's put this superpower to the test. We're going to use a classic equation of motion from physics. This formula describes the position of a moving object. Now, for this equation to be correct, every single piece of it, the x naught, the v naught t, and the 1/2 at squared, every single one has to have the same dimension. Let's see if it does.
Let's start with the easy ones. X is the final position, which is a length, so its dimension is L. Simple. X0 is the initial position, which is also a length, so its dimension is also L. So far, so good. The dimensions match.
Okay, now for the third term. V0 is velocity. That's length divided by time, which we write as L t to the minus 1. We multiply that by t, which is time, or just t. Now the t to the minus 1 and the t cancel each other out, and what are we left with? Just L. It matches.
And the final term, that 1/2 at the front, it's just a number. It has no dimensions. So we can totally ignore it for this. Acceleration, a, is length per time squared, or L t to the minus 2. We multiply that by time squared, t squared, which is t squared. And again, look at that. The t to the minus 2 and the t squared cancel out, leaving us with, you guessed it, L.
And there it is. Every single term in that equation simplifies to the dimension of length. The equation is dimensionally consistent. It passes our physics spell check. Now, the big takeaway here is that while this doesn't prove the equation is 100% perfect, that half could be wrong, for example, it proves the equation isn't impossible. It's a super powerful first line of defense against nonsensical physics.
So from the grand laws of physics all the way down to the numbers we see every single day, this language of units and precision is absolutely everywhere. So as you go about your day, look around. From a nutrition label to a weather forecast, what number are you going to see not just as a value, but as a statement of precision?